Greetings. Greetings. My name is Steve Miller. I'm a professor at Williams College. I am here with one of my assistants, and we are going to show you a fun game today called the I Love Rectangles game. And this game is going to give you some very interesting mathematics. So our goal is to explore tiling. So the first question is, what is a tiling? So imagine we have a collection of objects. We want to place them down to cover space. For example, we have a large 10 by 10 giant square, say 10 feet by 10 feet. What would be a good shape to use to cover it? We want the shape to be smaller than the big floor, and we want all the pieces to fit together.
1 by 1?
Oh, 1 by 1, that's a great idea. Let's use a bunch of 1 by 1 squares. So where should we put the first square?
In the corner?
Yeah, let's put one square down here in the corner. And where should we put the next square?
Next to it?
Next to it. And where should we put the next one?
Next to that?
And you can see that if we just continue adding like this, we will cover the entire 10-foot by 10-foot square. So building on our success as a fun problem, see if you can tile larger and larger regions with no gaps using the following shapes. So we have a triangle, a square, a pentagon, a hexagon, a heptagon. How many sides do you think a heptagon has?
7.
7. And an octagon? 8. And a nonagon would be 9, and a decagon would be 10. So note that each shape has all sides of the same length. We just saw we can do it with a square. Can you do it with a triangle? What about the pentagon? And when you put the shapes down, you can rotate them, you can spin them, but you have to put them together with no overlap, and so that there's no gaps.
You could do triangles in a triangle.
So you could do, okay. So now let's talk about the I Love Rectangles game. So if we have an unlimited supply of 1 foot by 1 foot squares, we saw we can cover larger and larger regions. So let's make the game more interesting. Imagine now we have exactly one of each size square. So we have only one 1 by 1 square, only one 2 by 2, only one 3 by 3, only one 4 by 4, only one 5 by 5, and so on. And the goal is we want to put them down one at a time so that we always have a rectangle. So again, we have to put them down one at a time, and at every moment in time, our shape must be a rectangle. So can this be done? And note that a square is a rectangle, so we could put down at least one of the pieces. So for example, let's say we put down one piece. Can we put down a second? So I suggest you pause right now and try to put down one piece and then see if you can put down a second. So I will let you try to do that. Good luck. Welcome back. What do you think the answer is?
No.
No. So let's say we put down the 4 by 4 square. So that gives us a rectangle because the square is a rectangle. Can we put anything next to it and still have a rectangle? So here's what we have left. We have a 1 by 1, a 2 by 2, a 3 by 3, and a 4 by 4. We have I'm sorry, not a 4 by 4, a 5 by 5. We already placed down the 4 by 4. We have a 6 by 6, but I haven't drawn it. I'm not going to draw everything. So imagine we tried to put the 3 by 3 next to the 4 by 4. We see it's not going to fit. There's going to be a gap. So there's no way the 3 by 3 would fit. And similarly, you could show none of the other shapes would fit as well. Uh-oh, so we're in trouble. We need to modify the game a bit. So we need to give at least one more square. What's the smallest square we can give?
A 1 by 1.
A 1 by 1. So we could do a 1 by 1 square. So can we do it now? So now we have two 1 by 1s, a 2 by 2, a 3 by 3, a 4 by 4, and a 5 by 5. I haven't given you that much more. So which should we put down first? Which should we put down second?
1 by 1.
So let's start off with put down one of the 1 by 1 squares. And now when we look and see what we have left, what should we put down next?
The 1 by 1.
Another 1 by 1. If we put them next to each other, we now have a 1 by 2 rectangle. If we have a 1 by 2 rectangle,
We should put down the 2 by 2.
we could put down the 2 by 2. So we're going to stop, let you think about this for a second, and see what can you put down next. Oops, and there should not be that 1 by 1 here. That should have been deleted. We already used that 1 by 1. So stop and see if you can think of what to put down next. And so if you put down the 2 by 2 square, we now have, we start off with a 1 by 2 rectangle. That was this one over here. Now we have a 2 by 3 rectangle. So what should we put down to continue a rectangle? We have a 2 by 3. So think about it for a while. You've got a 3 by 3 square, a 4 by 4 square, a 5 by 5 square, a 6 by 6 square. So stop and think. Okay, welcome back. So what did you think to put down?
The 3 by 3 because one of the sides is 3.
Yeah, the 3 by 3 because one of the sides is 3 and it fits perfectly now. So now we have 3 by 5. And now we still have a 4 by 4 square left. We have a 5 by 5, a 6 by 6, and so on. So stop for a moment and think, what can we put down next to this 3 by 5 rectangle and still have a rectangle? Okay, welcome back. We should put down a
5 by 5.
A 5 by 5. Now the 4 by 4 square does not fit, but the 5 by 5 does. And we now have a 5 by 8 rectangle. And so what do we have left? We have a 4 by 4, we have a 6 by 6, a 7 by 7, an 8 by 8, a 9 by 9, which I'm not going to draw, and so on and so on and so on. So what should we put now next to this 5 by 8 rectangle? So let's give you a moment to think. All right, welcome back. What should we put down?
An 8 by 8.
We should put down an 8 by 8. And now we have an 8 by 13. And let's see if you can figure out what the pattern is. So we're not going to use the 4 by 4, the 6 by 6, or the 7 by 7. So not every square is used, but it seems like we could always find another bigger square. So let's look at the sequence of squares we use. We used the 1 by 1, then another 1 by 1, then a 2 by 2, a 3 by 3, a 5 by 5, an 8 by 8, and so on and so on and so on. If we just look at the lengths of the squares, it's a 1, a 2, a 3, a 5, an 8. Do you notice a pattern? Well, this is an 8 by 13. What's the next one we're going to add?
13.
13. And so the next few terms in the pattern would be 13, then 21, 34, 55, 89, 144, 233. So I'm going to let you,
377.
so I'm going to stop and let you see if you can figure out the pattern.
And then 610.
So 377 is next,
Then
and
610.
then 610. All right, welcome back. Did you notice a pattern? Well, if we start with the 1, 1, notice that the next term, 2, is just 1 plus 1. And then 3 is 2 plus 1. And then 5 is 3 plus 2. 8 is 5 plus 3. 13 is 8. And we see each term is the sum of the previous two. And so now that you know this, hopefully you can continue the pattern. So these are called the Fibonacci numbers, and they have many wondrous properties. So there's this wonderful video that I'm going to show you now. So I'm going to toggle to the video. Here's the video. So this is about a 3-minute video, and it shows you all the different places the Fibonacci's are. So here's 0. So they start with 0, 1, 1, and each number is the sum of the previous two. So you can see 3 plus 5. 8 plus 13 is 21. 21 plus 13 plus 21 is 34. 34 plus 55 is. And they're showing us tiling, making larger and larger squares. Here's 1, 1, 2 by 2, 3 by 3, 5 by 5, 8 by 8, 13 by 13, 21 by 21. They're zooming out. And you see it spiraling around and it's getting bigger and bigger and bigger. And they're going to show you places where it emerges now. Where have we seen stuff like this? So you recognize what this should be. So you might notice this from seashells. amazing how many different places the Fibonacci numbers arise. Now what they're going to do here is a little bit more advanced. They're going to break things up a little bit. And so it turns out you can associate an angle to the Fibonacci numbers. So a circle, if you go all the way around the circle, that's 360 degrees. If you go around 137, that's about the Fibonacci angle. And what they're going to do is they're going to, like rockets, they're going to shoot a rocket or a plane every time we spin 137 degrees. And they're going to shoot more and more of these dots. And they're going to shoot faster and faster and faster and faster. And maybe you might start to notice a pattern. And so this pattern, which is related to the Fibonacci's, you see in sunflower seeds. And what they were doing is this ratio was coming from looking at dividing each Fibonacci by the previous. And that converges to about 1.6, and that's where this is all coming from. But the Fibonacci numbers occur in more than just sunflowers and seashells. So what they're doing here now is they're connecting different dots. And so they're doing some interesting connections. And you might notice that patterns like this emerge in wings of insects. So I hope you enjoyed the video. This is just the beginning. And actually, if you look over here, what shape is that?
Hexagon.
It's a hexagon. And so that hexagon goes back to what we were talking about earlier about can we cover things? So to just finish up, oops, wrong one. So just to finish up, let's go back to the share. And where is the, so what I want to do is I want to just finish up with one last thing. So this is an advanced thing. It's the Fibonacci spiral we saw a moment ago. And there's two different ways to calculate the area. What's one way to calculate an area of a rectangle?
Length times width.
Length times width. And so this rectangle is 21 by 34. So we could multiply 21 and 34. But this rectangle is also made up of a bunch of little squares. And if you have a square that's 1 by 1, its area is 1. If you have a square that's 2 by 2, it's 2 times 2, or 2 squared. 3 by 3, it's 3 times 3, or 3 squared. And if you add all these together, that's also going to equal this. So I hope you enjoyed this brief introduction to the Fibonacci numbers. Have a great day.